Once a problem area is identified, so let's say there's a repetitive task that a radiologist has to do 20 times a day, then it comes down to basically creative problem solving. How do you apply the tools that we have to either eliminating or mitigating that particular problem? And then you basically have to figure out which algorithms would work best and then get it to whatever acceptable standard you've set alongside the clinicians and then test obsessively, basically. And then you get it into the hands of actual providers and iterate until it becomes something that they can't do without, essentially.
The following is a conversation with Zack Allen, staff research and machine learning scientist at RAD AI. Zack's experience and portfolio is extensive, spanning from working on natural language processing models to more generally pushing the bounds of innovation and research with large language models and machine learning. Dear listeners, thank you so much for tuning in, and please join us in imagining the future. Thank you so much, Zack, for joining us today in the Imagining the Future podcast. Before we start delving into the questions, I'd love to hear a little bit about your background and what you do at RAD and why you came to RAD AI.
Sure, absolutely. Thank you for having me. So I'm a physician who transitioned into machine learning several years back, primarily in the language modeling area. I spend most of my work is at the intersection of AI development and clinical practice. And so what really, I guess, brought me to RAD AI is that they were doing lots of interesting things for very practical problems. And at the time, they were also very ahead of the curve. Essentially, they were doing generative AI before it became a buzzword. And so just constellation of all of those things was just made it a no-brainer decision to join.
Yeah, that's really interesting, actually. RAD AI has been working on generative AI far before it became mainstream, before it was even called generative, the initial transformer models. So that is fascinating that, it started almost very research heavy and then was trying to solve very practical problems. Could you maybe touch on that a little bit, what it looks like in terms of the academic versus applied research aspects as they apply to what you're doing and kind of what is it that the problems that you guys are trying to solve at RAD AI?
Sure. So the academic side tends to be much more towards trying to identify and push new algorithms, improvements to existing ones. There's a whole bunch of other interesting areas there, but a lot of those things don't transition extremely well into industry. So solving problems for populations like radiologists or other medical specialties, those tend to require much more domain-specific knowledge. And that's part of why we have, for example, our own clinical teams evolve so closely with the decision-making process. And so when it comes to solving those problems, you have to figure out ways, like you have to know, the domain well enough, and then you have to know the technology well enough to know whether it's appropriate to that situation.
Yeah, I can see why that's really important, especially in something like radiology when you're kind of trying to solve a pretty heavily impending crisis on the radiologist workflow. We hear a lot about how the workflow has become unsustainable for a lot of radiologists, given the amount of reads and volumes and just the administrative burden. So it's really interesting that the research team is able to find new ways to apply some of the cutting edge work to improving workflows. I guess, what do you feel like the research exactly behind the machine learning entails? Could you maybe tease that out a little bit?
Yeah, sure. So once a problem area is identified, so let's say there's a repetitive task that a radiologist has to do 20 times a day, then it comes down to basically creative problem solving. How do you apply the tools that we have to either eliminating or mitigating that particular problem? And once you've figured out, okay, is this a ML-worthy solution? So can AI help here? Then you kind of have to dive into really understanding the problem in depth, figuring out, do we have data for this problem? What would that data look like? And then you begin the whole technical process of turning that data into something that a algorithm can understand. And then you basically have to figure out which algorithms would work best and then get it to whatever acceptable standard you've set alongside the clinicians and then test obsessively, basically. And then you get it into the hands of actual providers and iterate until it becomes something that they can't do without, essentially.
Yeah, I love that process. I guess one thing that you said kind of triggered my thoughts here. You said ML worthy problem. I guess on that note, could you maybe talk a little bit about what exactly ML, which is machine learning, what exactly does that entail that makes something an ML worthy problem, and how does that differ from traditional computer programming?
Yeah. So I guess the classic adage is you don't use ML where something could be solved by a classical algorithm, so a rules based algorithm. So I guess touching on that, the difference between more classical approaches is you're sitting there essentially giving the program rules for every plausible situation. So if X, do Y is essentially what that boils down to. And then in machine learning, you're taking more or less an inverse approach to that of you don't tell the model what to do. You just show it lots of examples of what happened in reality, and it learns from the patterns in that data set. If something can be simply solved, you do just want to write rules for it. Whereas if it's a complex problem or there are lots of, say, edge cases, you want the more adaptive form from machine learning. The trade-off there is you are getting a little bit more uncertainty. So you don't have this entirely deterministic, guaranteed outcome in a particular situation.
That's really interesting when you talk a little bit about the edge cases and the complexities. So much of medicine, when I trained in medicine, one thing that they always tell us early on is that the practice of medicine is not a science. It's also an art. So it is as much of an art as it is a science because there are those edge cases and the complexities. It's not always A plus B is equal to C. There is a lot of detail to that. So I think based on what you're saying, it kind of makes something as complex as radiology especially so ripe for these more advanced approaches to problem solving. I guess on a more fundamental level, where do machines learn from? When you say like machine learning, what kind of data are we talking about, especially in the context of radiology and healthcare? Could you maybe talk a little bit about that?
Yeah. So, in a general sense, they actually learn from a lot of the same materials that humans do, in this case, physicians, right? So, if you're asking ChatGPT, what does this, that, or the other mean? It's going to give you an answer informed probably by a lot of the same textbooks that doctors have read. More specifically, in like Rad AI's context, it's learning from real world clinical scenarios. So we show it millions of scenarios where a radiologist has evaluated a chest x-ray, for example. And then it learns, okay, I've seen this pattern before. I need to put some approximation of that into my response. And so I guess up until very recently, most of these models have been learning from either images or text. We are starting to see a lot of what we call multimodal, so image and text, or really image, audio, and text. And then that informs how the model responds to the given situation.
Can you maybe give a real world example of this in practice, like what a radiologist using this might look like?
Sure. So one of our primary AI applications actually, the radiologist will enter findings straight from the image. So they will describe what they're seeing, and then the model will actually take that and produce the high yield summary called the impression. And that process used to require them to do lots of repetitive work. So they would basically be synthesizing that summary themselves. And now that is a component of the workflow that is taken over for them. So they no longer have to spend the time dictating that, thinking through the cognitive burden of actually producing it. And so that is a fairly confined snippet, but it's a highly repetitive process that they have to do on pretty much every report.
Yeah, that's huge, right? Because I think what people don't realize maybe is that something that is a crucial aspect of the radiologist's workflow and output is something that takes maybe, it seems like it doesn't take that much time, but when you have to repeat it over, say, 30 scans in the course of an hour over a 10-hour shift over 5 days a week, when you start to save a time and converting that into an automatic impressions, that's a huge, huge time save over the course of a shift and over the course of a week, which translates to thousands of hours over the course of a lifetime, and certainly significant ROIs. That is really interesting. What do you feel like are the biggest challenges that researchers face, and especially when we talk about something as complex as healthcare, but more specifically as radiology, because these are complex pieces that you're obviously dealing with. The research is new. It's all cutting edge. What are some of the complexities and challenges?
Sure. So I would say some of the challenges we face are much like any other machine learning problem. Real world data tends to be extremely messy. So if you have, very clean data on a constrained problem set, it tends to be very easy to build a solution for. Whereas healthcare data is coming from a bunch of disparate sources, there are different populations. Um, Institutions don't document things the same way, and they don't document them the same over time. So a lot of these factors can add a lot of noise when you're trying to teach basically an algorithm that learns strict patterns, if you will. Um, I would say we also have what we usually refer to as a long tail distribution of problems. So you have, say, 70 or 80% of things are made up by common scenarios. So let's say pneumonia, for example. That's a very common pathology that you'll see in radiology, right? There's then a very long list of things that occur maybe once in a million, right? That number's arbitrary here, but the point is a very long list of things that occur infrequently, and you have to find ways to, say, emphasize those to the model. So a lot of time is spent dealing with edge cases.
The quality of the models are essentially based on the quality of the data, to your point. And I guess it must be quite difficult in research to be able to figure out bias and fairness and those type of aspects as well. I mean, is that something that comes up frequently in this type of work?
Yes, bias is, of course, always a concern when you're building a machine learning model on a population data set because you don't know what underlying patterns might be there that will, say, make the model make a consistently wrong decision on a different population. And it's I guess always a concern in healthcare, but it's of increasing concern because there's obviously increasing scrutiny over AI as it takes over more and more operations. Rigorous testing is your best defense against those. Also, we train on very large, highly diverse data sets, which doesn't alleviate all concern on that front, but it does help heavily mitigate it in terms of, if we just train on an urban population and then try applying that to a rural population or, say, a different country, those things would probably not be best practice. So large, diverse data sets, you teach the model over the course of significant examples, and it kind of levels a lot of those things out.
Yeah, that's really interesting, especially because so much of this is an iterative process. It's not just here's a data set, learn, and then output. There's so much. I mean, that is why it's called machine learning, right? Because it continues to learn feedback loops and goes from there. I want to talk a little bit about overfitting, like the concept of overfitting. Now that we're talking about how training works, could you maybe talk a little bit about what overfitting refers to, if you see that happening, or kind of how you address that?
Sure. So, at a general level, overfitting can be thought of as the model learning the quirks of or maybe even biases of the training data too well. And so then when it goes to make a decision on, say, another hospital's data or inputs from another hospital, it might try to replicate those same quirks, and the two don't align, right? And so you're inducing systemic error there. And think about it as memorizing the wrong answer key to the test or something along those lines if you want. Um, so the best way to control that is, once again, well stratified, large scale data, but also test on whatever populations data you're going to be using it on and learn those things up front, preferably even train on some of that population's data, so that you're not biasing against those patterns. The other factor is have a close feedback loop between the real end user and your model generations. So when problems do arise, you take in that real world data feedback and have the model learn from a new set of data, basically.
I was thinking about when you were talking a little bit about curating it, I guess, to the end user. Um, One of the pieces of that impressions is the impressions product line is very strong because it is quite curated to the voice of the radiologist. Is that kind of what you mean when you say curate the products, or do you mean more in a general sense?
Some of both. It depends on where you're focusing. In the general sense, you need to ensure that it's focusing primarily on clinical stuff. You have to ensure that it's outputting medically correct. So, in our case, just focusing on impressions, for example, you have to ensure that it's outputting medically and contextually correct language. So, does this patient actually have the liver lesion or whatever it may be? And then, secondarily, you're also tailoring it to that radiologist's preference for how they would discuss that particular item. But in the general sense, first things first, everything has to be clinically correct. Then you apply personalization.
Yeah, I think that is a really, really interesting point because I think there's two aspects to successful models. I think as we think about the modern day of what um, AI, generative AI in healthcare has become is number one, first and foremost, the clinical efficacy and accuracy, because that's so important. But then now I think there's an increased appetite by consumers for that personalization.
Mhm.
And I think one of the coolest things that I learned about the impressions product early on was that so much of it is, of course, it is incredibly accurate, but also has so much personalization of being able to generate it in the radiologist's voice. So, that the accuracy piece also takes me to the concept of explainability and especially when applied to healthcare models. Can you maybe talk about, well, maybe start with how you would kind of explain the concept of explainability and how that applies in healthcare models?
Sure. So, I guess starting with the actual concept of explainability, in more classical machine learning models, and certainly in classical like programmatic solutions, you essentially have a direct decision tree, or you can trace a very close approximation of literally, if I start here, I walk through these decision points, and that's how I end up at my end result. Part of the problem that you get with large language models is simply the scale of the algorithm. So you're talking about something with billions of parameters. So, exponentially higher points of decision. And that level of complexity is very hard to decipher. So we don't currently have any truly explainability. We don't currently have any true way to draw out that same decision tree from language models. We do, however, have some ways to look under the hood and try and decipher at least what was influencing the various decision points. Um, One would be we can actually, due to the mechanics of how the algorithms work, we can actually look at what we call the attention and see where the model was drawing particular points of reason from. But there's still a lot of ambiguity around how did this point of attention lead to this particular output. I would say more recently, we have had other improvements. So we've recently seen the development of reasoning models. And so these are models that actually vocalize vocalize their thinking as they go to the final decision. So if you've ever used ChatGPT with one of these, you'll actually see a little box pop up and it will line by line go through its thought process. And tracing those, interpreting those is, I would say, a degree higher insight than we normally have, but it's not truly interpretable either. Um, Either way, backing out from like true interpretability, I would say the most important parts are know your training data very well. Once again, circling back to proper bias control, overfitting control, and so on. And at the end of the day, I would say principally we've seen providers care about the end result more than the actual step-by-step reasoning process. Um, just just personal experience there.
Yeah, I think there's a really important point in what you said. I think this entire aspect of explainability is new for everyone, I think, and the reasoning aspect. It's not just certain companies that are having uh, more time on this or less time. It's I think now we're seeing models evolve and even end users start to use more reasoning models. And often these are the models that are a little bit slower uh, and take more time because they're actually walking you through the decision tree and that explainability process. And it's certainly, I think, one of the more cutting edge areas of ML research because I think, it's almost like in elementary school when you had to show your work for arriving at the answer. At the end of the day, clinicians that are rapidly working through images at the hospital level may not always need to see the decision trees, but I think for the purpose of training a cutting edge model, it is really important to push the research forward on that. If you had to say what does successful machine learning in healthcare look like, what do you think that is, and what kind of evaluation methods do you use for yourself and the teams that you run, and especially in this larger ecosystem of um, machine learning in healthcare? What are kind of the bars that you hold for yourself?
That's a complex one. So I'd say there's two facets to that. The first is the technical metrics and performance of the model. So I have the set of outcomes that I know I want to happen within a particular evaluation set of data. How well are we doing on that? Basically, is the model technically accurate enough to be going into the wild? And what that threshold is, what those metrics are, varies heavily from project to project. I'd say in a more real world sense, is it moving the needle on a real world problem? So provider burnout, patient outcomes, follow-up rates, whatever it may be. Are you actually seeing the solution drive changes in outcomes on those fronts? And to be clear, it has to do some of both in order for it to be a truly successful project. Because if we're just producing a tool that's a fancy new technology, it's not really of practical use.
Yeah, I really appreciate that. I think, we talked a little bit about earlier in the conversation about how Red AI was working on these like transform models and Gen AI before it became mainstream, but really focused on this like key issue of, solving problems for radiologists in a very tactical way. And to your point, bringing on radiology expertise. So really for radiologists by radiologists is kind of the company's motto and really works through that. That's really important, I think. And I think that distinction between academic versus applied is so important because so much of the work now ends up becoming these academic tools that are technology for technology's sake, but how you apply them and what value you add after spending so many resources on it, I think is ultimately important. I guess one final question for you. What do you think the future of ML looks like? What do you think are opportunities to improve the field, and what do you think about ML in healthcare?
That's a very difficult question. There's a lot going on a lot of fronts. I would say, specifically in the healthcare field, we're going to see a lot more in the way of multimodal models. So, reasoning over multiple types of input data. So, you'll have the image, the text, and maybe even the audio straight from the radiologist. Who knows, right? You will also see, I think, more in the way of what we call longitudinal reasoning. So the model reasoning over not just the current scan, but the entire patient history. And I think longer term timeline for this one's a bit more difficult to decipher, but you will be seeing a lot more agentic systems. So systems that act much more like intelligent assistants across the entire workflow rather than point solutions that are, say, trying to help with this specific facet or that specific facet. So much more of a holistic workflow where you more or less don't even know that it's AI. It just feels like you're working with a junior partner or something along those lines.
Yeah, I think that certainly seems to be the trend, especially as I think we're all pushing for more generalized artificial and I guess super intelligence almost, where we're able to feel it's kind of rather than point of care solutions, it's like a wraparound service, and really being able to work with these type of um, products that can really feel very seamless in our daily workflows. I think that seems to be the future to me. Zach, thank you so much. This was such an insightful conversation. I learned so much about kind of not only the generalities of ML research, but how you're applying it at Rad AI and kind of the work that we're doing. So thank you so much for joining us, and my best wishes to you.
Thank you for having me.